So we are now in the Q&A session, and if anybody wants to ask a question, they can go to the microphone and ask, and we can start with the online audience questions, if there are any.
Okay, so the first question is, so what happens when the Hebden inequality gives you something trivial, like less than 2?
Well, it means that either the resources of the examples you have, the amount of data you have is not sufficient to guarantee any generalization, or, which is somewhat equivalent, that your tolerance is too stringent, okay? The situation is not really mysterious, okay? Let's say that you would like to take a poll for the president, okay? And let's say that you ask 5 people at random, okay? How can you interpret the result? Nothing, okay? You need a certain amount of respondents in order for the right-hand side to start becoming interesting. Other than that, it's completely trivial. It's very likely that what you have seen in sample doesn't correspond to anything out of sample.
So in the case of the perceptron, so the question is, would each set of W's be considered a new M? Okay,
so the perceptron, and as a matter of fact, every learning model of interest that we're going to encounter, the number of hypotheses, capital M, happens to be infinite. We were just talking about the right-hand side not being meaningful because it's bigger than 1. If you take an infinite hypothesis set and verbatim apply what I said, then you find that the probability is actually less than infinity. That is really, that's very important, okay? However, this is our first step. There will be another step where we deal with infinite hypothesis sets, and we are going to be able to describe them with an abstract quantity that happens to be finite, and that abstract quantity will be the one we are going to use in the counterpart for the Hebden inequality. That's why there is mathematics that needs to be done, okay? So I mean, it's obviously that the perceptron has infinite number of hypotheses because you have a real space, and here is the hypothesis, and you can perturb this continuously as you want. So even just by doing this, you already have an infinite number of hypotheses without even exploring further.
Okay, and this is a popular one. Could you go over again in slide 6 of the implication of nu equals mu and vice versa?
6, okay. Okay, this is, it's a subtle point, and it's common between machine learning and statistics. What do you do in statistics? What is the cause and effect for a probability and a sample? The probability results in a sample. So if I know the probability, I can tell you exactly what are the likelihood that you will get one sample or another or another. Now, what you do in statistics is the reverse of that. You already have the sample, and you are trying to infer which probability gave rise to it. So you are using the effect to decide the cause rather than the other way around, okay? So the same situation here. The bin is the cause. The frequency in the sample is the effect, okay? I can definitely tell you what the distribution is like in the sample based on the bin. The utility in terms of learning is that I look at the sample and infer the bin. So I infer the effect, the cause based on the effect. There is absolutely sort of nothing terrible about that. I just wanted to make the point clear that when we write the Hebden inequality, which you can see here, we are talking about this event. You should always remember that nu is the thing that sort of plays around and causes the probability to happen, and mu is a constant. When we use it to predict that the out of sample will be the same as the in sample, we are really taking nu as fixed because it has to be, this is the in sample we got, okay? And then we are trying to interpret what mu gave rise to it. And I'm just saying that in this case, since the statement is of the form that the difference between them, which is symmetric, is greater than epsilon, then if you look at this as saying that mu is there and I know that nu will be approximately the same, you can also flip that and you can say, okay, nu is here and I know that mu that gave rise to it must be the same. That's the whole idea, okay? It's a logical thing rather than a mathematical thing.
Okay, another conceptual question that's rising is that, so a more complicated model corresponds to a larger number of H's, and some people are asking, they thought each H was a model. So
Okay, so each H is a hypothesis, a particular function. One of them you are going to pick, which is going to be called G, and this is the G that you are going to report as your best guess as an approximation for F. The model is the hypothesis that you are allowed to visit in order to choose one. So that's the hypothesis set, which is script H. So, and again, but there is an interesting point. I'm using the number of hypotheses as a measure for the complexity in the intuitive argument I gave you. Not clear at all that the pure number corresponds to the complexity. Not clear that anything that has to do with the size really is the complexity. Maybe the complexity has to do with the structure of individual hypotheses and whatnot. And that's a very interesting point, and that will be discussed at some point, the complexity of individual hypotheses versus the complexity of the model that captures all the hypotheses. This will be a topic that we will discuss much later in the course.
Okay, and some people getting ahead. So how do you pick G?
Okay, so we have one way of picking G that already was established last time, which is the perceptron learning algorithm. Okay, so your hypothesis set is H. It is a script H. It has a bunch of H's, which are the different lines in the plane. And you pick G by applying the PLA, the perceptron learning algorithm, playing around with this boundary according to the update rule until it classifies the inputs correctly, assuming they are linearly separable. And the one you end up with is the declared G. So G is just a matter of notation, a name for whichever one we settle on, the final hypothesis. So how you pick G depends on what algorithm you use and what model you use, what hypothesis set you use. So it depends on the learning model and obviously on the data.
Okay, this is a popular question, although, so it says, so how would you extend the equation to support an output that is a valid range of responses and not a binary response?
Okay, so it can be done. So one of the things that I mentioned here is that this fellow, the probability here is uniform. Okay. Now let's say that you are not talking about a binary experiment. Okay. You can, instead of taking the frequency of error versus the probability of error, you can take the expected value of something versus the sample average of it, and they will be close to each other. And some obviously technical modification is needed to be here. And basically the law of large number, or the set of laws of large numbers from which this is one member, has a bunch of members that actually have to do with expected value and sample average rather than just the specific case of probability and sample average, which is also, I mean, if you take your function as being 1, 0, and you take the expected value, that will give you the sample as the sample average, and the probability as the expected value. So it's not different animal. It's just a special case that is easier to handle. And in the other case, one of the things that matters is the variance of your variable. Okay? So it will affect the bound. So you can, here I'm choosing epsilon in general because the variance of this variable is very limited. You know, so, like let's say the probability is mu, so the variance is mu times 1 minus mu. It goes from a certain value to a certain value. So it can be absorbed, it's bounded above and below, and this is the reason why the right-hand side here can be uniformly done. If you have something that has variance that can be huge or small, then that will play a role in your choice of epsilon such that this will be valid. Okay? So the short answer is it can be done. There is a technical modification, and the main aspect of the technical modification that needs to be taken into consideration is the variance of the variable I'm talking about.
Okay, there's also a common confusion. So why are there multiple bins?
Okay, so the bin was only our conceptual tool to argue that learning is feasible in a probabilistic sense. When we used a single bin, we had a correspondence with a hypothesis, and it looked like we actually captured the essence of learning until we looked closer and we realized that if you restrict yourself to one bin and apply the Hoeffding inequality directly to it, what you are really working with, if you want to put it in learning, in terms of learning, is that my hypothesis set has only one hypothesis. And that corresponds to the bin. So now I am picking it, which that's my only choice, I don't have anything else. And all I am doing now is verifying that its in-sample performance will correspond to the out-of-sample performance, and that is guaranteed by the plain vanilla Hoeffding. Now, if you have actual learning, then you have more than one hypothesis. And we realize that the bin changes with the hypothesis. because whether a marble is red or green depends on whether the hypothesis agrees or disagrees with your target function. So different hypotheses will lead to different colors. Therefore, you need multiple bins to represent multiple hypotheses, which is the only situation that admits learning as we know it. That I'm going to explore the hypotheses based on their performance in sample and pick the one that performs best, perhaps in sample, and hope that it will generalize well out of sample.
Okay, another confusion is, so can you resolve the relationship between the probability and the big H? So I'm not clear exactly.
Okay, we apply the, so there are a bunch of components in the learning situation. So let me get the, okay. So let's go for the, it's a big diagram and it has lots of components, okay? Okay, so one big space or set is X, okay? And another one is H. So if you look at here, okay, this is hypothesis set H, it's a set, okay, fine. And also if you look here, the target function is defined from X to Y, and in this case, X is also a set. The only invocation of probability that we needed to do in order to get the benefit of the probabilistic analysis in learning was to put a probability distribution on X. H, which is down there, is left as a fixed hypothesis set. There is no question of a probability on it. When we talk about the Bayesian approach at the last lecture, in fact, there will be a question of putting a probability distribution here in order to make the whole situation probabilistic. But that is not the approach that is followed for the entire course until we discuss that specific approach at the end. Okay. Question?
What do we do when there are many possible, say, hypotheses which will satisfy my criterion? Like in perceptron, for example, I could have several hyperplanes which could be separating the set. So how do
Correct.
pick the best?
So usually with a pre-specified algorithm, you will end up with something. So the algorithm will choose it for you. But your remark now is that, okay, given that there are many solutions that happen to have 0 in-sample error, there is really no distinction between them in terms of the out-of-sample performance. I'm using the same hypothesis set, so capital M is the same, and the in-sample error is the same. So my prediction for the out-of-sample error will be the same. There is no distinction between them. The good news is that the learning algorithm will solve this for you because it will give you one specific that one ended with. But even within the ones that achieve 0 error, there is a method that we will talk about later on when we talk about support vector machines that prefers one particular solution as having a better chance of generalization. Not clear at all given what I said so far, but I'm just telling you sort of as an appetizer, there is something to be done in that regard.
Okay, and a question is, does the inequality hold for any G even if G is not optimal?
What about the G?
So if G, does it hold for any G, no matter how you pick G?
Yeah, so the whole idea, okay, so once you write the symbol G, you already are talking about any hypothesis, because by definition, G is the final hypothesis, and your algorithm is allowed to pick any small h from the hypothesis set and call it G. Therefore, when I say G, don't look at a fixed hypothesis. Look at an entire learning process that went through the script H, the set of hypotheses, according to the data and according to the learning rule, and went through and ended up with one that is declared the right one, and now we call this G. So the answer is patently yes. G can be different, patently yes, just by the notation that I am using.
Also, some confusion. So with the perceptron algorithm or any linear algorithm, so there's a confusion that at each step there's a hypothesis, but
correct. But these are sort of hidden process for us. As far as the analysis I mentioned, you get the data, the algorithm does something magic, and ends up with a final hypothesis. In the course of doing that, it will obviously be visiting lots of hypotheses. So the abstraction of having just the sample sitting there and eyeballing them and picking the one that happens to be green is an abstraction. In reality, these guys happen in a space, and you are moving from one hypothesis to another by moving some parameters. And in the course of doing that, including in the perceptron learning algorithm, you are moving from one hypothesis to another. But I'm not accounting for that because I haven't found my final hypothesis yet. When you find the final hypothesis, you call it G. On the other hand, because I use the union bound, I use the worst case scenario, the generalization bound applies to every single hypothesis you visited or you didn't visit. Because what I did to get the bound of deviation between in sample and out of sample is that I considered that all the hypotheses simultaneously behave from in sample to out of sample closely according to your epsilon criteria. And that obviously guarantees that whichever one you end up with will be fine. Okay? But obviously it could be an overkill. And among the sort of the side effects, the positive side effects of that is that even the intermediate values have good generalization. Not that we look at it or consider it, but just to answer the question.
So a question about the punchline. So they say that they don't understand exactly how the Hevding works proof shows that learning is feasible. So
okay, the Hevding shows that verification is feasible. Okay? The presidential poll makes sense. That if you have a sample and you have one question to ask and you see how the question is answered in the sample, then there is a reason to believe that the answer in the general population or in the big bin will be close to the answer you got in sample. Okay? So that's the verification. In order to move from verification to learning, you need to be able to make that statement simultaneously on a number of these guys, and that's why we had the modified Hevding inequality at the end, okay, which is this one, that has the red M in it. This is no longer the plain vanilla Hevding inequality. We'll still call it Hevding, but it basically deals with a situation where you have M of these guys simultaneously and you want to guarantee that all of them are behaving well. Under those conditions, this is the probability that the guarantee can give, and the probability obviously is looser than it used to be. So the probability of bad thing happens when you have many possibilities is bigger than the probability that bad things happen when you have one of them. And this is the case where you add it up as if they happen disjointly, as I mentioned before.
Can it be said that the bin corresponds to the entire population in us?
The bin corresponds to the entire population before coloring. So remember the gray bin, I have it somewhere. We had a view graph where the bin had gray marbles. So this is my way of saying this is the generic input, and we call it script X, and this is indeed the input space in this case, or the general population, okay? Now, we start coloring it according when you give me a hypothesis. So now there is more in the process than just the input space. But indeed, the bin can correspond to the general population, and the sample will correspond to the people you polled over the phone, in the case of the presidential thing.
Is there a relation between the Hevding inequality and the p-values in statistics?
Yes, there are, I mean, so the area where you are trying to say that if I have a sample and I get an estimate on the sample, the estimate is reliable, the estimate is close to the out of sample, the probability that you will deviate is a huge body of work, okay? And the p-value in statistics is one approach, and there are other laws of large numbers that come with it, okay? I don't want to venture too much into that. I basically picked from that jungle of mathematics the single most useful formula that will get me home when I talk about the theory of generalization. And I want to focus on it, want to understand it in this specific formula perfectly. So when we keep modifying it until we get to the VC dimension, things are clear. And obviously, if you get curious about the law of large numbers and the different manifestations of in-sample being close to out-of-sample and probabilities of error, that is a very fertile ground and very useful ground to study. But it is not a core subject of the course. The subject is only borrowing one piece as a utility to get what it wants. Okay, so that ends the question here. So let's call it a day, and we will see you next week.